Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. Right? Within this module, we are trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within this second module, we are currently on the fifth topic, that is time sharing, right? So in the previous video, I described the concept of time sharing in detail, right? We talked about several different aspects of time sharing. And now that we have a good understanding of what is time sharing, before we go on to understand how the operating system implements this concept of time sharing, I want to talk about the origins of time sharing in this video, right? From the next video onwards, we will be looking at how it is implemented, right? What are the different aspects that we should think about, right? But before I delve into the implementation part, I want to spend some time on talking about its origins. So basically, computers were not always like the time sharing systems that we see today. It was quite different. And by understanding the like evolution of how we went from having how early computers were there and how they evolved into time sharing, it will help you to understand this concept a bit better, right? So let's talk about how early computers were there, how things used to be there before time sharing was like implemented, and how was the evolution, right? So let's talk about the origin and the overall evolution process in this video. So let us start the discussion with this diagram of time sharing, which we have already seen, right? So if you see this diagram, what is happening is that we have a computer system which has multiple processes, okay, right? And the number of processes is way more than the number of CPUs. Hypothetically, let's take this example where there is only a single CPU and there are n processes, right? So the problem that time sharing solves is that we have limited number of CPUs, and the number of processes is, or the programs that want to execute on the CPU is more than the number of CPUs, right? So to solve this problem, what operating system does is that it time shares the CPU among the different processes. Each process gets to execute on the CPU for some time, and then what happens is that the control of the CPU is switched from that process to some other process. And by frequently switching the control of the CPU, the operating system ensures that each process gets to execute on the CPU for some time and thus make progress, right? In this way, we are able to execute more programs and make progress for all of these programs using limited number of CPUs, right? So there is an illusion that all of the programs are executing, right? So here the time in the time sharing, the operating system will frequently switch the CPUs among all the processes, right? So this is the basic idea of time sharing, right? So if you look carefully, then there is a basic assumption here, is that in the system that we are operating, there are multiple programs that want to execute, right? Then only we need time sharing. If there is only a single program in the computer system, then there is no need for all of this switching, right? If there is only a single program, and let's say even if we have a single CPU, then that single program can execute on that single CPU, and there is no requirement at all for doing this time sharing. So time sharing is only needed when we have multiple programs in the system, right? So this is a very basic assumption that you should be aware of, right? So now the point is that computers were not always like this, right? We do not have multiple programs in running in the computer always in early computers. So let me give some examples. So in early computers, there used to be only a single program, and that single program. So early computers were kind of not so advanced as today, right? So they had a single program, and that single program had the entire computer system, all of its resources to use for itself, right? They were used to do some simple tasks like mathematical computations, right? So it was not a multi-program system. What I want to convey is that, and as I said, if there is only a single program in the system, there is no need for time sharing. So early computer systems were not time share systems, right? They were simple systems which had a single program running at any given point in time, and they had specific they were used to do specific tasks, right? And even today, if you see embedded systems, so embedded systems are simple machines. For example, take the case of the lift or the washing machine. These are embedded systems. Here they are very specific purpose computers, right? In contrast to the general purpose computers where you can do anything, right? You can write a program for doing anything. these embedded systems are very specific purpose systems. So for example, if you take the case of a lift, there is a tiny program running on a simple CPU, and the only thing that it has to do is that like take the it gets the inputs from the like the users, which floor it has to go, all of that lift management, that is the sole purpose. And that is why in the case of the lift, there is a single program running in that embedded chip, right? It has to just see which floor to go, right, whether the lift is overloaded or not, all these things, right, run the elevator algorithm. So it has a simple program, it has a single program. So again, let's take another example of an embedded system, that is the washing machine. A washing machine also has a simple chip, and it has a single program which only job is to take the inputs of the user, like, and calculate the load of the machine. It has a sequence, like it will bring in the water, run the machine, rinse the clothes, dry the clothes. It's a simple program, and there is the point is, in these embedded systems there is only a single program running. They are not like general purpose computers where you can do all sorts of things, where you can run different types of programs. They have a simple CPU with a dedicated program running a simple algorithm, right? So in these cases, and even in the early programs where there is only a single program in the system, so in these cases, we do not need time sharing. Since there is only a single program in these computer systems, we do not require to switch the CPU between multiple programs. So the point here is that early computers had only a single program, and even today, in cases like embedded systems, we have a single program. And these scenarios, these compute systems do not require time sharing. So let's first of all understand that how did we go from having a single program in the system to having multiple programs, right? So first, let's understand that part of evolution to understand the origin of timeshare systems. So what we will talk about now is that how did we go from having uniprogram. So uniprogram means a computer where there is only a one program at any given point in time, right? And so we will understand that how did we go from uniprogram to multi-program systems. Multi-program systems have multiple programs loaded in the memory at the same time. So this is the first step in the evolution. Let's understand this. So let us now understand that how did computers go from having only a single program, that is uniprogram systems, to having multiple programs loaded in the memory at the same time. So how did computers evolve from uniprogram systems to being multi-program systems? So for this, let's take a look at this time sharing diagram, right? So as you can see, there are three processes. This is an example for a time sharing diagram, right? There is a single CPU, and what the operating system is doing is that it is time sharing this single CPU among these three processes, right? Each of this process gets to execute on the CPU for some time. And we have seen these kind of time sharing diagrams in the previous videos also. So till now, in the discussion of time sharing, a basic assumption that we are making is that all the only resource that this process requires, or the only thing that the process does during its lifetime, is computing on the CPU. We have been focusing only on the CPU, right? But if this is not the true picture, in reality, processes don't just do computation. And we have talked about this earlier also, that processes spend time on both compute and IO. Both of these are very important parts in the life of a process. It's not just that you're computing on the CPU, because if you look at if you look at a program, if it does not take input or output, what kind of a program it is? If it does not take input, then every time you run this program, it will give the same output, because it is running on some static numbers or static data. It is not taking any fresh input. If there is such a program that does not take any input, it will always give you the same output. And you can imagine such a program is not really useful, right? Again, if you take another example, for a program which is only giving which does not give output, right? We talked about the case where a program does not take input. Now let's talk about a case where a program does not give output, right? Even if you run this program, it does not give you anything. So again, what is the point of running such a program which does not produce any output? The whole point of computation, right, at the very basics, we have talked about this, that the whole point of computation is that you give some kind of data as input. It could be in any format. The computer will do the processing, it will do the computation, and eventually you want some kind of output, right? This is the whole point of computation. So if there is a program that is not taking an input, or it is not producing an output, it is pretty useless, right? So the point that I wanted to make here is that till now we have been only focusing on the CPU as a resource, that this is the only thing that the process needs, but this is the only thing that the process does, but that is not the case. The process spends its time doing both computation and IO, and both of them take a major chunk of the process's lifetime, right? So we talked about the CPU IO burst cycle in one of the previous videos, right? So this is how the life of a process actually looks like. It starts executing with the CPU burst. Then the way this works is that now when the process has started, it will need some kind of input, right? Once it gets that input, right? Let's say this is a IO burst. Basically here, let's say the process has taken some kind of input, then it will do some computation with that input, right? And it will generate some kind of data. It will show that output to the user and again take input, right? This is the cycle that continues. It will get fresh data, it will do the computation, it will get the output, show it to the user, and this is how we as users interact with the computer system. We are giving it input, the process is doing the computation, and it is then showing us the output. So this is how the life of a process looks like. It starts with a CPU burst, then there are several alternating cycles of IO and CPU burst, and finally there is a final CPU burst and the process ends its execution. So the point that I want to make is that IO devices and CPU both are important resources that a process uses during its lifetime. So now let's we wanted to understand what how did we go from having single program to multi-program system. So why am I talking about input and output? Let's understand the consequence of this fact that a process, the life of a process is an alternating CPU IO burst cycle. This has consequences, and that will eventually from that we can understand that how that computers went from being single program systems to multi-program systems. So now let us take a closer look at the CPU IO burst cycle and understand what is the problem with having a single program in the computer system. So for this, I have this diagram. So on the x-axis, we have increasing time, and we have one process P1, right? So there are two resources. One is the CPU shown in blue color. The other is the disk, which is an IO device shown in gray color. So there is a process which is alternating between doing computation on the CPU and then doing some kind of operation on the disk, right? So for 10 units, you can see this process P1. For 10 units it is using the CPU. For then for another 10 units it is using the disk. This is a hypothetical example, right? So it is following the CPU IO burst cycle, right? So now if you look closely, what is the problem with this behavior of the process? So when the process is using the IO device, what happens is that the CPU is idle during that time, and we are talking about the case when we have a single program in the system, right? There is no other program in the system, and this single program, after doing the computation on the CPU, it has initiated an IO operation, and during that time the CPU is idle, right? You can see every time the process initiates an IO operation between 10 to 20 or 30 to 40 or 50 to 60, this is the time where the CPU is idle. So why is the CPU idle? Why can't this process do something on the CPU? The problem is that whenever a process requests for an IO operation, it could be initiating a read on the disk or a write on the disk, any kind of IO device. The problem with IO devices is that they are mostly mechanical in nature and they are very slow compared with the speed of the CPU. An IO device, the operation of an IO device is very slow, right? The CPU, the speed of the CPU is very fast. It is like it can execute millions and billions of instructions in 1 second, right? Whereas IO devices, the read operations take milliseconds, right? So the CPU basically can execute an instruction in a nanosecond or a picosecond, but the IO device is very slow. Operations on IO devices are around microseconds or milliseconds. So and another thing is that when the process initiates an IO operation, during that time it will block, right? It cannot execute, it cannot proceed with CPU execution, because let's say this process wants to read from some file. It will call the read system call, and until the data is available from the disk, the process cannot proceed with further execution, because the further execution depends on the data that is being read from the file. And as we just discussed, that read is going to take some time since IO devices are slow, so the process is blocked during that time. So what happens is that in this case, let's say the process is doing some computation and it initiates a read on the disk, let's say. So the process will block in this case, it will take some time to read it will take some time to read from the disk and make the data available. And during that time, until that data is available, the process is blocked and there is nothing to do for the CPU. So that is why the CPU will be idle. And once the data is available, then the process unblocks itself. It can do computation with that data, it can process that data, and again, let's say it initiates a read or a write operation. In that case, again, it will block. It will during this time when the IO device is reading or writing the data, the process will be blocked. And the point is, IO devices are slow and these idle times can be very long. In this diagram, I have shown equal CPU burst and IO burst, but in reality, IO burst times can be very long and this waiting times can be very long. So the problem with this is that now this leads to poor CPU utilization, right? Since there is only a single program in the system, and when it blocks during that time, the CPU is idle. The this computer system which has only a single program, its CPU is idle for most of the time, right? And this is kind of wastage of the precious resource that we have. So the whole problem with having just a single program is that it will lead to poor utilization of the CPU, and not just CPU. If you look closely, even the IO device is not busy for most of the times. So the point is that a single program is not enough to keep the CPU or even the IO busy. So what I have done, as you can see, I have introduced another program into the system, which is process P2. So what we are doing here is that so this was the case when we had a single process. Now we have another process. So whenever the CPU is idle, right? Whenever the CPU is idle, we are executing that other process P2. So now you can see the CPU is always busy. So CPU utilization is always CPU is always being utilized, right? And the problem that we were facing of poor resource utilization is solved. So the key point here is that we need to have multiple programs in the system, right? So with multiple programs, CPU and IO operations can be overlapped, thus improving the utilization of all the resources in the system. So you can see how by overlapping this during this time frame, you can see when process P1 is doing basically doing an IO operation on the disk, the CPU was idle. So we allowed process P2 to do computation. So process P1 is doing, you can see the process P1 is doing IO operation and process P2 is doing a computation on the CPU. So we are overlapping computation on the CPU with operations on the disk. Both of them are happening at the same time. So this ensures that the resources are utilized properly, right? So by having multiple programs in the system, we improve the utilization of all the resources, not just CPU. We can we can also have the case when process P2 is doing process P1 is doing computation, this process P2 can do IO operation, right? I have not shown it, but here when P1 is doing computation, P2 can do IO, and when P2 is doing computation, P1 can do IO. So both the CPU and the disk can be fully utilized, right? So the whole point of this example is to show you what is the case when when we have a single program in the system. You can see when we have a single program in the system, most of the time one of the resources is idle, either the CPU is idle or the disk is idle. By having multiple programs in the system, we can overlap CPU and IO computation. We know that all the processes will follow the CPU IO burst cycle, right? It is the behavior of the process to do some computation and then do some kind of disk any kind of IO operation, right? So each process will display the CPU IO behavior, and by having multiple programs in the system, we can always have some process using the CPU and some process using the IO devices, and thus the overall utilization of the system will be high. So that is why we went from having a single program in the system to having multiple programs in the system, right? So this is something to give you an analogy. Let's take the case of cooking. When you're cooking, a single dish often does not require your attention all the time. Thus, you are kind of underutilized. So one can cook multiple dishes. So let's take an example. Let's say you are cooking rice and you put the rice in boiling water, and that's it. So when the rice is boiling, in that time you don't have to do much, right? So you are kind of idle. So to optimize things, to do things in a better way, you can do something else in that meantime. You can start chopping vegetables, right? So by overlapping work, right? In case of cooking, on one side the rice is boiling and on one side you're chopping vegetables. So by overlapping things, you can optimize your utilization. Is good utilization, right? So in this case, this is very similar to the case of the computer system. when we are using CPU, when one process is using the CPU, the other process can use the IO devices, right? So this is one analogy where you can understand how by overlapping things you can improve utilization, right? So in this case, in the case of cooking one single dish can is not enough to keep you busy. So cooking multiple dishes, and by overlapping things you can improve the utilization, right? So initially in early computers, we had a single process in the computer system, right? But we saw the problem with this is that the overall computer like utilization of the resources, whether it's the CPU or it's the IO devices, is low, and we do not want that. These resources are expensive and they should be utilized properly. So to improve the utilization of the system, multiple programs started, like the concept of multiple programs being in the computer system at the same time emerged, and this concept is known as multi-programming, right? What is multi-programming? Multi-programming means having multiple programs loaded in the memory, each ready to execute. So we have the memory, all of these programs will be loaded in the memory and each of them is ready to execute. And so one of the processes will be using the CPU, some will be doing IO computation. The point is that there are enough programs and there is enough work to keep all of the resources, whether the CPU or the IO devices, busy, right? Which is not possible when we have only a single program in the system. So having multiple programs is very crucial because there will be enough work and we can switch between things, we can overlap computation and IO operation. So having multiple programs is very crucial uh, to keep the system properly utilized, and this concept has a formal term. It is called multi-programming, right? Another thing is that the number of programs in memory is known as degree of multi-programming, right? So let's say you have 100 programs loaded into the memory at any given point in time, then the degree of multi-programming is 100. So this is a term, right? So we started with the case when early computers had only a single program in the system, and we call it uni-programming. Uni means one. So early computers were uni-programmed, right? And the problem with uni-programmed was that the system was not properly utilized. So there was evolution from having single program in the system to having multiple programs in the system. So we evolved from uni-programming to multi-programming, and the requirement was, or you can say the benefit was, improved utilization. So the necessity was to improve the utilization. That is why we had this evolution from uni-program systems to multi-program systems, right? Now moving on, one question that I'll ask is that, is multi-programming and time sharing same? Is having multiple programs in the computers, is it the same as time sharing? The answer is no. Time sharing is much more than multi-programming, right? Just having multiple programs is not equivalent to a time share system, right? A multi-program system just has multiple programs, but a time share system is much more than that. So let's understand what is the difference between multi-programming and time sharing, and how did we evolve from multi-program systems to time shared systems. So now let us discuss the difference between multi-programming and time sharing, right? So the first difference is that the aim of multi-programming is just to improve the system utilization. And we saw how this is possible. When there are multiple programs loaded into the memory and all of them are ready to execute, we can have, when one process blocks on the CPU, let's say, and it starts doing IO computation, then some other process which is ready to execute can be brought in into the CPU and start executing. In this way, by overlapping computation on the CPU and operations on the IO devices, we can have a good CPU like system utilization. So having multiple programs, the goal of multi-programming is to improve the system utilization. Now coming to time sharing, the aim of time sharing is a little bit different thing, right? So the aim of time sharing is to provide an illusion of multiple programs running at the same time. So what does this mean? So this means that, let's say you are using a computer system and you are interacting with multiple programs. So you want to the user has to be given the feel of an interactive system, right? When they're interacting with multiple programs, each of them should be responsive, right? So the illusion of multiple programs running at the same time, to achieve this, what time sharing systems do is that, as you can see in the next point, they switch at very high rates, right? So the control of the CPU is frequently switched between multiple programs, right? And by giving a chance to each of the programs frequently, all of the programs can make progress. and this gives the illusion that all of them are running at the same time. And we have seen this. It might not be the case, and it is often not the case that the number of CPUs is sufficient to handle the number of programs. Even when the number of programs is way more than the number of CPUs, what we are doing is that we are switching the CPUs frequently between all of the programs, and all of the programs can make progress, and it feels that each of them is running simultaneously, and thus the user is given a feel of an interactive system where none of the program is like lagging, right? Whenever they are switching from one program to another, each of the programs are responsive. So this is the concept of time sharing, right? Here the main goal is not to improve the system utilization. Obviously, since we have multiple programs in the system will be fully utilized, but the goal is much more than that. Apart from utilization, which is just a consequence of multi-programming, time sharing is an extension over multi-programming. It is like a superset. It is more than multi-programming. In time sharing, we have this added feature that the system with having multiple programs, each of the system like the each of the programs is given a share of the CPU. Each of them make progress, and the user is given an illusion that all of the programs are running at the same time, right? And for this, the next point, that is switching point, it is very important. In case of time sharing, the switching is done proactively, right, at a very high rate. Like hundreds of processes will be switched in 1 second. Whereas if you talk about multi-programming, here the switching is only done when it is required. It is a reactive approach, right? So when a process blocks or it terminates, and when the resource is free, only then we need to switch to some other process, right? So in case of multi-programming, when our only goal is to improve system utilization, when one of the resources becomes idle, then only we switch to some other process. Then only we bring that other process into the picture. Whereas in time sharing, the switching of processes is done proactively. We do not wait for the resource to become idle. We are doing the switching at very high frequency, so that all of the programs get to make progress, and the illusion that is provided to the user, that is all of the programs are running at the same time, can be maintained. The goal of time sharing is to give a feel of an interactive system, a responsive system to the user. In multi-programming, it could be the case that there are multiple programs in the computer, but one program is doing computation for a long time, and it does not give up the CPU. If that is the case, then the other programs that are there in the system, they will not get a chance to make progress, right? So if the goal of the system is just to improve utilization, then there could be the case that other processes are kind of not getting the control of the CPU, and there is one process hogging the control of the CPU. Other processes could also get starved, right? They might not get a chance if the computation is very long. So this is the difference between the switching strategy of multi-programming and time sharing. In multi-programming, the switching is done on a need basis only when it is required. When the resource is idle, then only it's done. And this could mean that one process makes progress, the others do not. And in time sharing, the switching is done at a proactive basis at a very high rate, so that all of the programs get to execute, get to make progress, and the illusion is created that all of them are running at the same time. The system becomes responsive to all of the programs, right? And there is a relation that let's talk about the last point. Multi-programming can happen without time sharing. It's a subset, right? It's a smaller concept, whereas time sharing is a bigger concept. But so the point is that multi-programming can happen without time sharing, whereas the vice versa is not true. Time sharing cannot happen without multi-programming. So what I'm trying to say is that if you have multiple programs in the system, then we have a multi-programming, right? But if we do not do switching, then we do not have time sharing. Only when we add the switching concept, switching of the processes at high frequency to this concept of multiple programs, then we get time sharing. So multi-programming is a subset. Time sharing is an extension over multi-programming. So multi-programming can happen without time sharing. You can have multiple programs loaded in the memory, but there is no need to switch, right? And still multi-programming is there. Your system utilization is good. So the goal of system utilization is achieved, but the illusion of multiple programs running at the same time, that will not be achieved. Only when you add the switching strategy at high rates, then we get time sharing, right? Also, the reverse, that is, time sharing cannot happen without multi-programming. So the fundamental requirement of time sharing is that you should have multiple programs in the system. Only then you will talk about switching, right? So first and the foremost criteria for time sharing is you need multi-programming. And here the thing that I wanted to say is that if you can just have multi-programming, there is no requirement to switch. But if you start switching, then you have this added benefit that the system is responsive. The user who is using the system and interacting with multiple programs, they'll get the feel that all of the programs are running at the same time. So So this is the last point, that multi-programming can happen without time sharing, but time sharing cannot happen without multi-programming. So coming to the question, is time sharing the same as multi-programming? No, time sharing is an extension over multi-programming. Multi-programming is just having multiple programs in the system, and the goal is to improve the system utilization. The switching is done on a need basis. Whereas in time sharing system, the fundamental requirement is that first of all you have multiple programs, and not just care about utilization, you also care about the interactiveness of the system. So you do frequent switching of the multiple processes. So this was the difference between multi-programming and time-share system. So now we'll see how multi-programming systems evolved into time-sharing system. We, in the first part of this video, we talked about how we went from having single program systems to multiple programs. Now let's see what was the reason for evolution from multi-program systems to time-sharing system, right? So now let's discuss how multi-program systems evolved into time-share systems, right? So let's start with this fact that early computers were very expensive, right? And unlike today, where modern personal computers are affordable by many people, it was not the case in early days. Early days, computers were very expensive. They were large, and again, they were so a few other points is that they were non-interactive, less accessible, and used batch processing for jobs. So let's discuss each of this point. So we talked about the expensive part. These computers were built custom, and they had special purpose, like they have a special task, right? And these occupied even large rooms, so they were very expensive, right? It was not affordable by everyone, and it was not meant to be personal computer like we have today. Like everyone today has a computer, like many people have their computer. This personalized computer experience was not meant to be in the early days. It was, in early days it was still maturing. The device itself, the computer itself, was maturing, and it was under research. So those were large computers, not meant to be used by a single person, right? So they were expensive. Second thing is that they were non-interactive, right? So what does it mean that they were non-interactive? Basically, like we sit in front of the computer today and interact with the computer, give it input, it does some kind of processing, gives us the output. This sitting in front of the computer part, right, this interacting with the computer as it is computing, was not present in early computers. So the way it used to work was batch processing. So like users, generally in office scenarios, people did not used to have computers at homes. First of all, it was purely at academic and office uses, right? Like today we have portable computers, computers at home. That was not the case. Computers were used in defense, research, academia, office, only in these scenarios where it was affordable, right? And so what happened is that there were many users of a computer, and they would submit their job, right? They will write their job, basically their program, on a set of punch cards, right? And they would submit their jobs to an operator, right? Early operating systems were actually humans. They used to be called operators, and that human would be operating that device. So many people would submit their jobs and then go, right? That operator will load all of the jobs into the machine, and the machine will execute those jobs one by one. So this was a non-interactive experience. So once that so there was a waiting time, right? Once that jobs is completed, let's say after 4 to 5 hours, the users who had submitted their jobs will come to the operator to collect the output. This is how computing used to be there in early days, when there was batch processing systems. You submit your job, you go on to do something else. It will take some time depending on the load of the duration of the job, the load in the system. It can take an entire day also, and then after the job is done, then you can come and collect your output, right? This is how the interaction with computer used to be there. It was non-interactive and less accessible, obviously. As I said, uh, people did not have personal computers, people did not have computers at their homes. It was a large device, very expensive device, which used to be used in academia, research, offices, right? So this is how early computers were there. We are talking about multi-program systems, that is fine, right? But if you look at this multi-program systems, although multiple jobs are loaded into the system, it is a non-interactive system, right? Also, it is not accessible. So this was the state of things. Then there was this new idea of a time share system. This new idea of a time share system was that we have a large computer and it is very expensive. So what do? We share that computer between multiple users. So what initial time share systems, how they used to work is that there was single large machine, right, and multiple small terminals. So as you can see in this diagram, there is a single large computer, and it has it has a good capacity, right? It can support many users. So what used to be there, multiple terminals were attached to this big computer, this expensive computer, and many users could now use the system in an interactive way, right? So this is the idea, this is how time sharing originated. So the idea is that since the machine is large and it is not accessible, right, it is non-interactive. To solve all of those challenges, we had this initial time shared systems. So this large machine, since it's shared between many users, now it is, the cost is going down, right? It is interactive because now users are sitting in front of a terminal, and lastly, it is more accessible now. Previously it was only in offices and you had to give your job to an operator, so the accessibility part was also low. So with this new concept where a large machine with many terminals and users sitting in front of terminal, this was the concept of time sharing. So as you can see, how will the time sharing system work? All of these users who are sitting in front of the terminal, they will give their programs, and these programs will be executed by the machine. Now, since multi-programming is not the issue, having multiple programs is not the issue. This machine is very well capable enough, right? It can execute multiple programs, right? Now the problem here is that uh, now these users are sitting in front of the terminal. They also demand interactive performance, right? When you're sitting in front of a terminal, when you submit a job or when you submit a program to execute, you want it to be executing in an interactive way. You want to interact with it. You do not want to have that user experience where you submit the job and the it is lagging or it is sluggish. So uh, in this time sharing system, basically when the users are sitting in front of the terminal, there is an important requirement, that is they demand interactive performance from the system, right? All of these users are sitting in front of the terminal. Earlier it was not the case. They would just submit their job and there was, the expectation was that okay, it will take a lot of time and you can go. But now, since the users are sitting in front of the terminal, they also demand interactive performance. So all of these users are submitting their jobs, or you can say giving their programs for execution to the system. And this system is responsible for not only executing all of these programs, but also giving all of these users an interactive experience. So what will it do? It will frequently switch between different jobs, right? For example, here there are three users, and this computer system has three programs. It will frequently switch between all these programs so that each program can make progress, right? So so that each of this user feels that their job is getting executed. So basically the experience that has to be provided is that all of the users should feel that their program is running, right? It is not the case that only one user program should get executed for a long time and the other two users are waiting for their output. That is not the case. In this new environment, this computer has to provide this user experience that every user feels that their program is getting executed. So to do that, this time shared system has to frequently switch the jobs, right? Each of the programs will execute for some time and thus make progress. And by frequently switching the CPU between different programs, uh, this illusion, that is the fundamental illusion we have talked about, right? This illusion will be created that all the programs are executing at the same time. That is what the users want. Since we have multiple users, all of them should feel that their program is executing. So this fundamental illusion that time sharing systems create by switching between different jobs frequently is that all of the programs, this illusion is that all of the programs are executing at the same time. Obviously that is not the case. That is just an illusion that is created by frequently switching between different jobs. So you see how from having multiple programs in the system, there came a need for an interactive experience. That interactive experience was due to the fact that now users are sitting in front of the terminal, right? The computer is more accessible. The computer is more interactive. Due to this expectation on response time, or you can say expectation on interactiveness, we have this requirement of frequent switching between jobs. In both early systems, when we talked about batch processing systems, right? In both these cases, we had multiple programs. In this batch processing also there was multiple programs. Here also we have multiple programs. That has not changed. They are both multi-program systems. But with time shared systems, what has changed is that now users are sitting in front of the terminal. That was not the case in this one. Here users would come with their jobs, submit their jobs, and then go away, right? All those multiple jobs would be executed, but there was no interactive experience. But now we had the demand for an interactive experience, because the computer is being shared by multiple users who are sitting in front of the terminal. So that is why this frequent switching part came, right? And now finally, also one more thing is that this concept of time sharing has now evolved into personal computers. So as computers grew faster and cheaper, personal computing was possible. And now, even though your personal computer is being used just by you, right? In the case earlier, one computer was shared by multiple users, right? To provide the interactive experience for multiple users, it has to switch frequently. But now computers are cheaper and they're accessible for everyone. People have their computers at homes, they use it personally, their device is dedicated to them. Still, since you are now running multiple programs, time sharing is still relevant. It is so that time sharing now evolved into time sharing within personal computers, right? So in a modern computer, you are doing running multiple applications, you are interacting with all of them. So all of them have to be run like in a time sharing manner, so that you get a responsive system, right? It should not be the case that you're running one application, it is responding, but the other one is stuck. So what happened is that the time sharing for multiple users evolved into personal computing also, so that when now you use the computer, you're running multiple applications, and those multiple applications are time shared, so that you get the experience that all of them running at the same time, right? So this is the evolution of time sharing. So let's summarize what we discussed. We had computers where there was only a single program in the computer, that is uniprogramming. Then we basically discuss the fact that a single program is not sufficient to keep the entire system properly utilized. The resource utilization is not good, right? To fix that, we have multiple programs in the systems. When we have multiple programs, we can overlap the usage of different resources, and that leads to good resource utilization. So the need for improving the utilization led to the evolution of multiprogramming. And now multiprogramming is time sharing is more than multiprogramming. We have discussed this fact, right? In multiprogramming, the switching of jobs or switching of programs is on a need basis, right? It is only when there is a resource is idle, we can switch to some other job. But now, as we discussed, when users started sitting in front of the computer, right? When there was a demand for an interactive system, that led to the evolution of time sharing systems. Here, not only we have an improved utilization due to multiprogramming, we also have an improved response time. We have a responsive system, right? So this is how the evolution this is how we evolved from a single program computer to multi-programming, and finally to time sharing. So you see, time sharing is an extension of multi-programming. It not only provides utilization, it also provides a interactive experience. So guys, this was about the origin of time sharing. Now you understand how what exactly is time sharing, right? And how it evolved from early computers when we had just a single program, right? So this gives you a good base for understanding time sharing. And in the next video onwards, we'll start discussing how time sharing is implemented. We have now covered what is time sharing and what was the origin of time sharing. From the next video onwards, we'll discuss how exactly it is implemented by the operating system. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.